Hi, in this video, we'll talk about the reduced density matrix and the partial trace. Now, we know that if I have a combined system, let's say in HA tensor HB, if I have a pure state, psi AB, then it is separable if this can be written as a simple tensor phi A tensor gamma B, right? This is a separable pure state. But how does this concept work for mixed state? So if I have a mixed state, let me denote by a density matrix rho AB, then it turns out that this is separable if I can write this as a sort of linear combination of a state in the first subsystem, tensor product, the state in the second subsystem, and PIs are probabilities, right? And the idea is that a state is separable. Let's say you have Alice and Bob, which are that are separated, and you have some classical communication between Alice and Bob. So this is classical communication channel. Now, if Alice has a state, so they initially start with a let's say a joint state, and if Alice is able to manipulate her state, Bob is able to manipulate his state, and there is also a possibility of classical communication. If they start with an initial separable state, they will end up with also a separable state. So the idea is that you cannot generate entanglement with classical communication and local operations. So this is LOCC, local operations and classical communications. So this is an example of a separable state when you are concerned with density matrices. The main point of this video is to tell you how to compute the partial trace and come up with the reduced density matrix of one of the subsystems. In a simple case where the state is pure, the reduced density matrix of the first state is obviously just so for this first example over here, the reduced density matrix of subsystem A will be just this, and similarly for subsystem B. In the case of the density matrix, the reduced density matrix is going to be just the of subsystem A is going to be summation pi rho AI, and rho B is going to be summation pi rho BI. So, but in general, if the states are not separable, it's not so obvious how to compute this density matrix corresponding to one of the subsystems. For that purpose, let's suppose I have a pure state psi and an observable A. You know that the expectation value of this state when it is measured by this observable is this bra psi and A psi, right? And similarly, if I have an initial density matrix and I measure it with observable, so this is a state and this is observable. So if I measure now a density matrix, the expectation value of A when it of this density matrix rho when it's measured by observable A is just trace rho A. So that's the setup. But suppose I only suppose I have a bipartite system. So let's say I have to begin with, I have a bipartite system, and I measure only the first subsystem. So I have some measurement operator that only acts on the first subsystem. So I have MA tensor identity. So it doesn't do anything on the second subsystem. And I want to compute this expectation value, right? So the question is, does there exist a state? So this is question mark. Does there exist a state of system A that gives the same measurement statistics as this? So only measuring subsystem A when you have a joint system, does that give the, is there a density matrix of subsystem A that gives you the same measurement statistics? And if such a thing exists, I will call it the state. So this state A is, I will call this as trace over subsystem B, row A, B, and this is the partial trace. So it turns out that such a partial trace or operation or the reduced density matrix, so this will be called the reduced density matrix, does exist. The matrix, and the operation to find out is the partial trace. So let's move on to computing the partial trace operation. So let's next we look at partial trace. So partial trace. So the partial trace operation should take a density matrix from the combined subsystem and either give a density matrix on the first subsystem. So this is if you do a partial trace over subsystem B, or it should give you the a density matrix in the second subsystem or subsystem B if I do a partial trace over the first subsystem, right? So indeed it is an operation. So trace over B, the subsystem B, is an operation from the density matrix of HA tensor, so HB, to B of HA. And similarly, partial trace over the first subsystem is, so B of HA and B of HA, which means the matrices in Hilbert space HA and B of HB are the matrices in Hilbert space HB. So this partial trace over the first subsystem or subsystem A should give you the density matrix of in the second subsystem, right? So the way the partial trace operation is defined is in the following way. So suppose I have partial trace over B and I have this sort of simple operator A1. So this is an operator in subsystem A, tensor B1, B2. Then if I take the partial trace over subsystem B, then this is defined as A1, A2, and trace of B1, B2. We call this tracing out the second subsystem. So this is also equal to A1, A2, and inner product of B1, B2. So, and then you, by linearity, you can extend this operation to any operator in HA tensor HB. So that's how the partial trace is defined. Now, let's try to compute the reduced density matrix of a combined system where the initial state is in an entangled state. So suppose, so we are trying to compute the partial trace of this state, which is initially in this entangled state, so 1, 0. So this is a state in C2 tensor C2, and let's try to compute the partial trace over the subsystem A. So it will give you a state in subsystem B. So first thing to do is to write the density matrix of this pure state. And this will be just the projection, which I can write as, so this will be, if I write this state, it will be just 0, 1, tensor 0, 1, minus 0, 1, 1, 0, minus 1, 0, 0, 1, and plus 1, 0, 1, 0. So this is the density matrix. Now, the partial trace is linear. So I will, if I take the partial trace over subsystem A, let's say, so if I take trace of A of this entire thing, then, so suppose I do a trace of A over row AB, then this is going to trace out the first subsystem. So this will be, let me do B, because the previous example I had done the second subsystem. So, okay, so this, suppose I do the partial trace over the second subsystem, then this is, I can write this as trace over B. So I can write this state as 0, get 0 bra 0, tensor get 1 bra 1, right? And then similarly, I can write the other state. So this will be minus 0, 1, and tensor 1, 0. This is for this one. And minus 1, 0, tensor 0, 1, and plus 1, 1, tensor 0, 0. Right. So now I can take in this whole operation by linearity, and I can, so this will be 0, tensor 0, and then trace of, so the first one over here will be trace of 1, 1, and then the second one will be 0, 1, and then trace of 1, 0, and then minus 1, 0, trace of 0, 1, and plus 1, 1, trace of 0, 0. This is just by the definition given previously of the partial trace operation. Now this trace is equal to 1. This and this is equal to 0, this is equal to 0, this is equal to 1. Okay, so I have missed out a half because I have this state which is square root of 2. So I have missed out a half over here. So this should all be half, right? So this is half times. Anyway, the point is that I can cancel out this and this because the trace is 0 in over here for both. So this gets half 0, 0 plus half 1, 1. And this is a density matrix. So I can write this as half identity over half over 2. So this is actually called the mixed state, or maximally mixed state, maximally mixed state. Right. So, and if I do the same operation by taking the partial trace over subsystem A, then again you will see that you will also get this state. So this is, I should say that this is a state of subsystem A. If I do the operation on subsystem B, so trace over A subsystem row AB will also lead to identity B over 2. So this is again a maximally best. This is a very interesting property when you start with this type of entangled state, the maximally entangled state, if you take partial trace over any of the subsystems, it leads to a maximally mixed state. Now, there is also another way to do the same thing, and it's also eliminating because it just deals with matrices. So if I have a state rho A B, then I can always write this as a summation over ij, Eij tensor Aij. So for example, what I mean is that suppose I have a, a state, a density matrix in C2 tensor C2, then it will be a 4 cross 4 matrix. I can divide it into blocks of uh, 4 matrices of 2 cross 2, and let me call them A11, A12, A21, and A22. And this Eij, so E11 is just the matrix with one in the one entry in the top left and zeros everywhere else. E12 will be 0, 1, 0, 0, and E21 will be 0, 0, 1, 0, and E22 will be 0, 0, 0, 1. So I can always do that for a density matrix. And Aij are not necessarily density matrix. So now if I do a partial trace operation, so suppose I do a partial trace over subsystem A, so I'll get a state in subsystem B of this row AB, then this should be, by the definition, it is equal to summation over ij trace of Eij multiplied by Aij. That's how we define the partial trace operation. But notice that only two of the four these Eijs have trace 1. The rest of them are 0. So this is actually equal to summation over I Aii. Okay, and on the other hand, if I do a partial trace over the second system, I should get a state of the uh, sorry, if I do a partial trace over the second system, I should get a state in the first subsystem. So I should get row A. This is trace over B, row AB. So now if I do that, I should get, so I have my initial state over here. I should get summation over ij, Eij trace of Aij. Right. So let's look at a 4 cross 4 matrix. So these are two equations that uh, um, let's look at an example of a 4 cross 4 matrix. So let's take row AB is equal to row 1, 1, sorry, let me just write, is equal to, let's write this as A11, A12, A13, A14. So let me just write this matrix, which is a density matrix in C2 tensor C2 for A31, A32, A33, A34, A41, A42, A43, A44. So now, suppose I have this density matrix, then if I look at this block matrices, so if I want to compute row AB, then it's just summation AII. So row AB, so look at this equation, row B will be, so this is A11, this is A12, this is A21, this is A22. So row B will be A11 plus capital A11 plus capital A1. So this will be A11, A12, A21, A22 plus A33, A34, A43, A44. Right? That will be row AB. So this will be equal to A11 plus A33, A12 plus A34, A21 plus A43, and A22 plus A44. This will be the reduced density matrix of subsystem B. Now, if I look at the equation, this equation over here, the reduced density matrix of the subsystem A will be given by this equation over here, right? So if I look at it, it will be, so you have to take the trace of these A11s and multiply with EIJ. So it will be, so let's start taking the trace. The trace of A11, capital A11 will be A11 plus A22. So this will be row A will be A11 plus A22 multiplied by E11. So this will be 0, 0. Then for A21, this will be, trace will be A13 plus A24 multiplied by 0, 1. This is E12. And similarly, we'll have plus the trace of A21 will be A31 plus A42 multiplied by E21. And finally, A33 plus A44 multiplied by E22. So row A will be equal to, so row A will be equal to A11 plus A22, A13 plus A24, A31 plus A42, and A33 plus A44. So this will be the partial trace of, so these two equations represent the partial trace. So this is, sorry, this is row B of over subsystem A and subsystem B respectively. So these are the reduced density matrices of subsystem A and subsystem B. Okay, so what we learned today was a slightly difficult concept. It's the ability to find the reduced density matrix of initially given joint state, but the joint state may be itself either a pure state or a mixed state. In the example that we gave, it was initial pure state, which was in an entangled state, and we found that it was the reduced density matrix of this entangled state was in fact the maximally mixed state. Now, it turns out that it's a conundrum of quantum mechanics that suppose you have an initial state. So suppose you have a initial state is equal to this entangled state, then you pretty much know everything about this state because it's a pure state. You know what sort of the probabilities or the probability amplitudes are. But if I take the partial trace or compute the reduced density matrix over any subsystem, then it becomes a maximally mixed state. In fact, the maximally mixed state can be written as um, a mixed combination of any two vectors, orthogonal vectors, orthonormal vectors v and w, and there is a complete sort of not at all complete information about this state. In fact, if you measure any of the subsystems in any basis, then you will lead to it will lead to this maximally mixed state, which is pretty much no information about that state is known. Even though we know the complete, we don't know the partial information of any of the subsystems.